Hi, everyone. Thanks for having me again. Today's talk is titled Clojure Remixed, in which we're going to take a look at something new my company is working on named Pyroclast. We'll take a look at what's going on here and specifically what the relationship is between Pyroclast and the Clojure programming language itself. I think you'll find it to have quite an interesting parallel. So it's good to be back. I've been kind of off the conference circuit for a while, being heads down, doing a lot of building and thinking, and I'm really happy to share what we've got today, because this is the first time in 10 months we're going to show off what we're doing here. My name is Mike Drogalis, and you might recognize me as the creator of the Onyx platform and also the CEO of Distributed Masonry. So like I said, today's talk is about our next product, Pyroclast, and to some degree how we built some of the particularly challenging pieces in Clojure, but more around the fact that Pyroclast has been designed to offer Clojure's core value propositions to everyone in a very intentional way. Pyroclast really is the next logical step for Onyx. We're almost at the end of the 0.10 release, for which we did a complete rewrite of the internal streaming engine, as well as all the plugin interfaces to set up for what we're doing here. So there was a lot of upfront effort to get Onyx in shape to do something a lot more commercially oriented. And I definitely wouldn't say that Onyx is feature complete by any means. We continue to work on it. It receives lots of attention. But I feel like the core maintainers can start to shift our attention from being strictly in internal maintenance mode to maybe building something on top of it that's a little bit more targeted in a wider audience. So when we were evaluating what we were going to do next, one of the obvious paths was, well, why not make Onyx properly available in multiple programming languages beyond Clojure, because you can use it from other JVM languages, but it's not pretty, and non-JVM languages at this point is a no-go for a whole bunch of reasons. And I think we could tackle this. We can do it in parallel. It's a great goal, and we should. But I also think that there's opportunity to do something significantly bigger, because Onyx from the outset was designed to have a unique level of flexibility in both in the way we model our distributed data processing programs, as well as its runtime execution. And I think if you exploit that properly, you can really push the envelope for the kinds of systems that we're building and maybe usher in a new generation of distributed systems. So to that end, we've opted to build something new named Pyroclast, which is built directly on top of Onyx, that exposes Clojure's core value propositions to everyone, not just Lispers this time, but to any developer who's doing stream processing. And this time, it's a closed source effort, but my objective today is to show what we're doing at the stream processing level and how I genuinely believe this would not be possible without Clojure, at least given the constraints in terms of time and money for our team. So today's talk is going to have three parts. We're going to look at what Pyroclast is, to give you some context as quick as I can. And then we're going to look at how Pyroclast is mimicking Clojure in that very particular way. And then I'm going to talk in depth about how we're actually able to do this. Before I jump into what Pyroclast does, I'll frame it in terms of what you do. If we look at your architecture for a moment, you have at least one database, probably more these days, a set of applications, some APIs, and maybe you're subscribing to event streams yourselves. And these entities, as they run, are either producing or receiving data as a byproduct that we'll call event data. It's generating data about things that happened. And a really common goal is to take that event data and apply a set of functional transformations, filters, and reductions over it into a data processing pipeline, if you will, with the goal of getting it into a pristine shape or form that is usable either by those original generating applications or other downstream applications, so that you have this sort of self-sustaining architecture where it's running and it's learning from itself. And you can build all kinds of systems like this. And the idea was that we wanted to pick a strong candidate use case for Onyx and make a proper platform as a service around it, because there are some concerns that you really should not properly scope at the distributed streaming level and need to be handled at the application level. But if you're doing a platform as a service, you have a little bit more leeway to do a more holistic approach. And so the idea was we wanted to do this, either a data pipeline-esque application or sort of a CQRS application, and do it really well out of the box and make it really simple. And like I said, there are things, no matter what you pick, Onyx, Spark, Flink, doesn't matter. There's going to be really difficult territory in getting this right. It's not impossible, but it's probably more work than you think it is if you haven't done it before. Step one, getting your data off of your source of emission and getting it into your data pipeline can be tricky, because you maybe have to be doing some back pressure because your data pipeline's overloaded or it's transiently offline for a couple seconds. And so your tools need to be able to checkpoint that data locally and ensure that it's eventually going to get into the data pipeline, because if you can't do that, you can't get the right answer in terms of doing reductions and aggregates. So step one is actually even somewhat difficult. As far as being able to tune performance, even if you're really not doing high performance event streaming, you may run into situations where you have a disaster and you need to do a backfill. I don't know, maybe you need to backfill 100 million events in a day, and that's the worst time to find out that you really don't know how to tune your system, because then you have two problems. I think the most difficult piece, though, is recovering state during either a code redeployment or a failure. Traditionally now, we're just replaying the entire event stream, which it's fine, but it can either be really expensive, it can be impossible if you can't recover the original event stream. There's a whole bunch of reasons why it is worth trying to figure out a strategy for having less downtime, at least in terms of your ability to catch up on the state, but maybe you can't afford to have stale state as you're rebuilding your materialization of those aggregates. And then finally, there's just the whole idea of your monitoring infrastructure and having good DevOps, because this is a distributed system, and there's a lot of hard-earned knowledge to be able to keep one of these things up. And so Pyroclast, if I was just going to put it on one slide to sum up, kind of as quickly as I can, is a fully hosted cloud platform for building real-time event streaming applications. And the idea is that we are able to ingest your event data into our permanent storage, and we'll stream it through data pipelines which you have defined, and we'll run for you, and then we'll push that data back to you. If you did a bunch of functional transformations over them, we'll push it back into your stack. And also, we'll expose microservice endpoints so that you can get at your reduced state as it streams. And the idea behind having a microservice instead of talking directly to storage is that you won't have visibility if we need to do a transition of how we're doing it, or if we need to be offline for just a little bit, we can make sure that it's at least stale within a particular bounded amount of time. And what you get when you do this is streaming as a service. And this is really exciting, because now it's very easy to do things like data cleaning. You can put Pyroclast at the front of your architecture and then have a set of services downstream, and you can ensure that you're going to get access to that pristine shape of data, and it will kind of be by contract correct. It's good for enrichment, so taking your data and changing it in particular ways to add or adorn it. High precision continuous queries, because underneath Pyroclast is actually a CQRS architecture, so we are streaming your data over queries immediately as it enters the system, which means it has the property of having constant time read access. And that's really nice if you have to offer that as an SLA in your architecture. And as well, just things you use Onyx for, it's good for analytics and doing event series aggregations, those more mundane things. And just before I jump into why, just to make sure it's totally clear, because we're going to look at some stuff in a minute. It's easy. Your application on the left has a set of language bindings, and you are pushing into our cloud. Everything on the right is essentially a black box, and we're just flowing into a data pipeline. And then you can access microservices through an endpoint that we're going to offer per deployment, and you'll be able to pull that back in your stack. So it's meant to be really easy. And that's probably enough context for what it is to move on to the story behind the relationship between Pyroclast and Clojure. And I would say that there are 4 pillars that are connecting these two things together. A really good sense of interactivity, a strong set of functions out of the box, and models for dealing with state and time. These last 2 in particular are really important for reducing the amount of complexity. And if you can replicate those ideas that we have at the language level and then turn them into something that is contract-oriented at the platform level, you can make a lot of people's lives easier. And so these 4 things have analogs. They exist in Clojure, and we have built things to sort of mirror them in the streaming domain. And I wrote the talk to discuss these 4 concepts, and I did slides, and I went through my talk, and it was 2.5 hours. So we're just going to talk about interactivity this time. So if you want to know about how these other things work, I've got the material, and I'm ready. So interactivity. It sounds simple. Clojure has a REPL. We use the REPL, end of story, right? Maybe not. It's worth thinking about. So why do we really like it? It's easy to explore how something works. Under the contract that I give you A, input A, you're going to give me output B. It is a throwaway environment for trial and error. Unless you're doing something that's side effecting on the world, you feel isolated, like you have this sandbox where you're kind of containing everything. And it's what makes Clojure so pleasant to use. But I think a non-obvious critical property is that it has really fast turnaround time, because the time it takes to receive your output is no longer than the time it takes to actually invoke the function. I mean, I was talking to Alex Miller this morning. We were just talking about Java way back when, and it was like, I can't write another static void main or whatever it is, and to test this, it's just going to drive me insane. And then Clojure came around, and it was like, oh, this is fantastic. So the idea that we're able to experiment really fast is a critical property. If you look at event streaming platforms and these kinds of distributed data processing systems, REPLs don't really exist. I mean, Spark has a REPL, but it's not in the vein that I'm trying to get at. Because I believe that the hardest problem with event stream processing is actually understand what's going on as it runs. Because in a normal local program, you have a call stack where you call f of x, and then you eventually get a return value, and it's kind of just moving up and down the stack. But with event streaming, we model things traditionally as directed acyclic graphs. So you have a value that's sort of going to copy and split itself, and it may go in divergent directions. And if there's a problem at some lower branch in the DAG, it's actually quite cognitively difficult to figure out what went wrong upstream to sort of fix that behavior. And I think what exacerbates this is that the dev test deploy loop is soul-crushingly slow for most of these systems because they require a full AOT compilation to be able to patch your program as they run. I mean, there's sort of techniques for getting around this, but it's just a fundamental problem of the way these things are architected. And this is why Onyx's deployment model is the way it is. I get asked that, like, why not do it exactly how Spark and Flink and Storm do it? And the reason is that we need to cut down this time, because if you're under that approach, doing an Uberjar is like at least a minute for a non-trivial project. I think it's 2 minutes for our project. And if you're going to re-upload to the cloud and go from your laptop to like EC2 or something, that's 2 or 3 minutes. And by that point, I'm on Twitter, I'm doing something stupid, and I come back in 10 minutes, and then I forget what I was doing in the first place. And that happens to everyone. And so we're trying to cut down the feedback loop from minutes into milliseconds. And I think a secondary but equally important goal is to enable deep introspection. And by that I mean, I give you input A, you give me output E. If something went wrong in the middle, what were B, C, and D up to? To make that a little bit more clear, if I have function f and I pass in value 6 and I get 12, and I didn't expect 12, and then I go looking at the function definition of f, and I see it's gh of I, rather, maybe I peel it apart and I realize that h of g of x actually got the wrong value. Notably, I of h of g of x doesn't even matter at that point because it got a value that really it wasn't supposed to. So the rest of that is essentially useless to me. What I need to do is unfold the stack. And we have tools like that for like light table, and now Cider is doing that. But it's a little bit more nuanced when you're working with a DAG. Just to visualize that in case I lost you, because it's a really fundamental point. If I have f of x and I get x star, what I want access to are the horizontal stripes. I want to see how x max to x star and y to y star. So that's if the call stack is going down and the return values are coming back up. I need that linearization of matching values. So Pyroclast is trying to make this better, and we're trying to provide a solution here. This is really one of our core tenets that's supposed to reflect, it delivers on the promise of Lisp that we have interactivity everywhere. And we call our REPL the simulator. What we wanted to do was come up with a method of assembling data pipelines very rapidly and the ability to find errors as you author them. Not after you deploy, not after you test, or that doesn't make any sense. You know what I meant. Yeah, anyway. So when we're deciding where we're going to actually run this, we talked about Emacs, we talked about maybe running this in IntelliJ, but really the browser wins when you need to do rich data visualization. And so this is kind of the place to be. And like I said, the goal is to understand what happens if a specific piece of data enters my pipeline. What are the repercussions to that? And the simulator's goal is to be able to take a pipeline and then attach some of your sample data to it. And on every action that you take, that changes the pipeline, we're going to recompile your pipeline and then run your sample data through it and display the results with deep introspection with very high fidelity. And by that I mean, if it says it's going to do this in the simulator, it better do that on the distributed cluster at runtime. Achieving that parity is really hard, but you need to have accuracy so that, I mean, if you don't believe it, then it has no point at all. And the effect is that Pyroclast is actually maintaining a shadow distributed systems program that is recompiling and re-executing on every keystroke. And that's a big claim, but I'm going to show it now, and hopefully my demo works. This is a pretty involved demo, and I am running the full stack locally because I don't trust the Wi-Fi. I have to figure out how to move Windows. Yeah, there we go. Oh, I can't see it on my laptop now. This is going to be really hard. Does anyone know how to mirror it?
Yeah, display preferences.
Preferences? Oh, where's my cursor? Okay. Thank you.
should be good. Okay, good.
Wait, where did my window go? Oh, there we go. Okay, great. Now it's huge. Thank you. Okay, so this is Pyroclast. When you log in, you're able to create topics, which are places you're able to push data to, very much akin to a Kafka topic, and you can create services, which are constructions around topics where you're able to build a pipeline and then access those microservices that I discussed. And so we're going to create a new service, a demo, create the service. And what you see is a two-layered approach. On the left, you're able to craft your data pipeline and set its configuration. And on the right is the simulator. And we're going to show how that works in a minute. Through the middle is a visualization of the data pipeline and actually how your data flows through. So the first thing, at the head of every data pipeline is a topic to read some messages from. Just because we're sort of messing around here, I don't have to pick a topic. It's pretty lax about that. And you can choose a functional transformation, an aggregate, or a filter. And you'll notice that these functions should look very familiar. And that's because Clojure has a wonderful API, and it works, so let's not throw it away. We've added some more functions from Java, as well as some of our own, just to be able to cover most cases, as well as arbitrary JavaScript. And so just to get started, we're going to do the frequencies function. And I'm going to say that we want to run frequencies across the message key. The simulator needs to have a wide variety of ways of interacting with it to target more specific and more coarse-grained scenarios. So if I don't know what the frequencies key does, I have a doc string here. It says returns a map with the distinct keys from the target array to the number of times they appear. Very similar to Clojure. And the idea is that I can give it any record, which is going to work with JSON. And I can say that message is my target key. And I can say hello world. And as I type, it's going to go ahead and update for me. And what's nice is that I can explore. Like, does it work with capitals? And does it matter if they are capitals? It does. It's case sensitive. How about white space? It's pretty cool. Symbols, spaces, more symbols. This is a really nice way to explore. Now, I left this destination key empty, and that's because by default, I'm just going to overwrite the key as I apply it in place. But I could just as easily say, put it in this output key. And so I've retained the original message, and now I've done the structural modification, which will let you sort of move your data a little bit better. One interesting thing here is that we're mindful that a lot of data is nested now, and you may have to move things up and down hierarchies. So we implicitly support get-in and association everywhere. So if I did double bracket and then I did X, it's actually just going to go ahead and understand that and be able to put it down into the specific nesting level. So that is the most targeted way to work with the simulator. But I want to have that deep introspection. If I know all these functions, what I'm doing, I have a purpose, I have a goal, I'm going to go ahead and try to maybe apply some kind of a transformation to a piece of data. So if I'm working with something that says message is Clojure West, Portland, 2017. Now, the pipeline is highlighting blue, meaning that data is flowing through it successfully. If we had a filter that was like removing records that didn't match a predicate, the line would halt and not be blue. So it's a visual indicator of what's going on. And I'm just going to tear it apart. I'm going to maybe do split by white space. And I'm going to take the message key. And you'll see it splits it into a vector of 3 elements. And if I put these together, they become 1. Bug, no bug, bug, no bug. Kind of cool. I'll continue. So now I have a vector of 3 elements, but I don't really like this being positional. What I would really like is a zip map over message. And I would like to zip it against the keys conference, city, and year. And so now I have those as key values. And they're still under the message key. They're one level down. I don't really like that. I want to move them to the top. And so again, structural manipulation is really important because we don't know what we're dealing with. So now I'm going to say I'm going to move message. And it's going to move them right to the top by default. This is a little bit of a divergence from get-in. We needed a way to specify what it means to go to the very top of the map, so double bracket is how you do that. But if I wanted to say nested under X, it's going to know how to put it under that particular key. And I can nest arbitrarily or go into vectors. It's a good way of doing positional transformations. And I guess just to finish it off, if I was going to do something kind of useful, I want to turn that last value in an integer, so I can say here's my cast map, and say that year is most definitely an integer, and I get the right answer. I can fold these things up so it's really easy to understand and look at it. Maybe I want to do Conch was in Austin last year, 2016, and it's going to go ahead and change. And I had these folded up, but really these are all changing as we go. And so this is what I'm after. This is what we want to be able to do and change how we perceive event stream processing. Now, this is pretty cool, but considering one piece of data at a time is limiting. When we work with larger amounts of data, we work with reductions and aggregates, and we want to understand how we're able to compound pieces of data into smaller chunks. So what I'm going to do is I'm going to remove all these tasks, and I'm going to do something else. Delete, delete, delete. I'm going to remove this. And we're going to look at some sample data from, I just made up this file. This is a set of players who are playing a game. They have a name. They have an event time when an action happened. They scored points, a number of points from a particular position. And what we want to do is an analysis over this data set. So what I can do is switch the simulator mode from text mode to file mode and drag my sample data file, drop it here. It says I've loaded up 198 records. Cool, good to go. Now I'm going to start doing some stuff. I'm just going to do one aggregate so I could keep my demo moving along. We give it a name because we were able to query this reduction through an HTTP endpoint, so I'm going to say I'm going to sum points. And show of hands, how many people are familiar with Google Dataflow and the windowing abstractions? Not too many. So I'm going to teach you now with what I believe is the only interactive method of looking at a data flow visualization. So there's multiple ways to do an aggregate. We're going to start with the simplest one, which is a global aggregate, which means give me all data. And we'll do a sum over all the points. And that says, cool, I got 9,924 points in your data set. Pretty simple. We just ran all the events through, did a quick sum. And to be clear, so this is a helpful way of understanding how your program is going to behave when we deploy it. When you deploy it, we don't actually get access to this. You get access to a microservice, which gives you the backing raw data. But this is a handy cue for figuring out what your program is going to do. But if it stopped here, it wouldn't really be all that interesting because, I mean, this is Excel, right? Just do a sum. But maybe a little bit more interesting is we're going to group by key. I want to know how many points each player scored. And so I could say group by name, and this will understand what that means and go ahead and switch it to a bar chart. That text is very small. We are still figuring out how to do that for good interface design. But now we have Ron, Greg, Cindy, Sally, and Fred all playing the game, and they have a particular number of points each. And so it's showing me what the actual backing data is as a visualization, because that's a lot easier to understand than just the raw text. So still, that's not terribly interesting, because that is taking all the data and then applying one function to it. The really powerful kind of analytics are able to tap into the event timestamps of each piece of data and then logically group together pieces of data that occurred around the same time. So we're going to change this to a fixed window. I'm still going to sum all the points. And now it's going to ask me for a window key, which says, give me the key in your map that represents the time that this event occurred. So that was, in my data set, event time. And the last thing I'm going to pick is the range. Range is a unit of measurement per time that's going to sort of tumble forward. So if I say I'm going to do a range of 3 minutes, what's actually going to happen is that I'll get a timeline here with these blue boxes. And if I zoom in, you'll notice that these boxes are exactly 3 minutes long. So every piece of data will fit into a 3-minute interval. And this is very different from a SQL query where you're just going to group by a certain number of minutes. This is actually able to backfill at runtime which 3-minute slot it is filled in, either forwards or backwards from the Unix epoch 1970. And so it's able to track that with constant time. What you'll also notice, there's two things. This white space means no data has occurred here. So as I'm zooming in, my bar chart's just totally empty. And as I'm zooming out, these bars are actually changing because it's only showing what's within my particular range of view. So again, if I zoom in, I'll see that, that text is terrible. These time bounds are exactly 3 minutes apart. So it's saying within this 3-minute interval, this number of points were scored. And automatically you're able to slice by time. More interestingly, again, we'll group by key again. We'll do it by player, because now I want to know what happened on a player-per-player basis per 3-minute interval. And I get a split timeline for each of my players. And again, I have these boxes which are more dispersed now because each player was sort of folded into one timeline earlier. And as I zoom in, again, I'm going to get these graphs changing. these timestamps now are reflective of 3-minute ranges, but they're showing each player. So now I have a quantitative analysis per category that I group by. So this is pretty powerful right out of the box. The last thing I want to demo is something called session windows, and these are the most complex to understand, which makes having a data visualization really helpful. And the idea behind sessions is that we're going to pick a session key, which is going to denote whose session it belongs to. And the idea of a session is somewhat like a streak, where a group of data happened, and we set a particular timeout where if data happened within that timeout, we extend the session. So you could understand that a session is maybe a logged in period for a user, because we don't have explicit login and logouts anymore for mobile applications. So if we're receiving event data, we can really only tell when a session of you playing the game was when we received events. And so this is one method for doing that analysis. So again, if I say my session key is name, and I give it a timeout gap of 20 minutes, I'll get that same timeline. But now these blue boxes are not of a homogeneous shape. You'll notice that Cindy has a longer blue box here between about 1437 and 1550. I can actually get the exact numbers if I wanted to look right here. But this indicates that activity occurred here as number of events within a 20-minute time boundary. And on the white, the spaces where I see white, specifically in here, there was no data to be able to collapse these two sessions together. So presumably, if there's more than 20 minutes of inactivity, that constitutes two different sessions, under which we're going to take the sum of their points. So we figure out how many points they scored per session if I don't have any sort of other indicator. And this sort of analytics is really difficult to pull off, because you need to be able to dynamically resize windows as you receive data, specifically from the past, because those windows are going to merge as you receive either old or new data. The last thing I can do is group by key. Now, instead of grouping by name, because I've already done that with the session key, what's very interesting is that I could group by the position in which they scored and get some really targeted analytics. So now I have the sessions for which each of my players scored from the center, from the left, and the right side of the screen in 20-minute sessions. And if I go ahead and extend that timeout gap a little bit further, now these sessions are growing. You'll see that they've enlarged a little bit, because there's a longer period during which they could have idle activity before we collapse those sessions together. Again, if I zoom in, now I have a specific analysis of when Cindy was scoring from the center between 1534 and 1636, and these aren't estimates; these are exact. They're able to grow and to the corresponding timestamps in either direction. How am I doing on time? Not bad. There's one more thing I wanted to show. I'm not sure if it's going to work because I slept my laptop, and like I said, I'm running the whole stack locally. As I said, you don't get these graphs when you launch. I've already launched a service to pick up Slack messages from our room, and so when you launch, you get something like this. These are collapsed. It's saying I'm doing an aggregation where I'm counting messages over a fixed interval, and you get this endpoint. So I could say copy, and now I can do, there we go. Let me do a couple things here. Size that up, turn that into HTTP minus myauth for a little bit more readability. And so this is an example of what you get when you run a service. You can tap into this, the actual backing data. And so this is a block in your architecture. This is in Tableau, where you have a nice visual front end. This is something where you put at the front to receive your data, and you build services around. And it's a nice tool for making sure that your state's going to upgrade correctly, that your services will be online, and that your analysis is going to be correct if you give us the right data. And so that is all I have for my demo so far. Let me talk a little bit about how all of this is actually working, because that's interesting. I've lost speaker notes now. Nope. Nah, that's fine. I don't really need my notes. Okay. Like I said, so 10 minutes left. Okay, so you probably have questions about how exactly the simulator works, and I'll try to address these and leave time for questions, so I'm going to have to go a little quick and assume some knowledge. What is happening is that this is actually an entire Clojure stack. At the bottom, we're running everything through Kubernetes with Datomix serving the runtime for the simulations that you saw. We have all the metadata stored in Datomic because that makes a nice data contract to be able to move around the stack. This is obviously built on Onyx, and we're using DynamoDB to store windowing contents. At the top of the stack, we're using Onyx, Untangled, and a web worker to be able to make this move quickly, as well as some local caching. But the secret is that a lot of this code base is actually written in CLJC. All of the functions that you saw me invoking have corresponding implementations between Clojure and ClojureScript. And it wasn't as simple as just using them directly because there are some minor differences. And the idea was to get isomorphic behavior, where if you get behavior in ClojureScript, you should get that behavior in the JVM. Now, we can't do this always because things like Clojure or JavaScript's type system make that really hard with integers, but that's not really something worth chasing, in my opinion. This is a two-step process to be able to make the simulator work and work really quickly. So if you notice, it was, as I was typing, there was very little lag. It was not talking to the network. It was not talking to the internet. It was staying directly in JavaScript the whole time. And to pull that off, you need two things. Number one, you need a really, really fast compiler, one that which we wrote in CLJC. And this is the thing that maintains the shadow copy of your distributed systems program that is going to mirror your data pipeline and keep parity. What's interesting about the compiler is that it doesn't use any code generation at all. It's a data-to-data compiler, so it's more of a loose term than like a hardliner compiler sort of design. But what's important about this is that if you use code generation to pull this off, it wouldn't be fast enough because you'd have to generate a verbose amount of stuff and then sync it to the server and to run it somewhere, and that just doesn't work. So that part will not port. Also, it's hard to reason about generated code. I think everyone here knows this. So if you generate data structures, you're going to have a heck of a lot easier time understanding what it is you have produced in the first place. Like I said, the compilation target is data structure, and that's useful because it is amenable to incremental compilation. So as I type in those text boxes, we know which part of the pipeline you've changed and can thus just recompile the minimum amount to make it work. Data structures are amenable to compression, so that's good for saving on memory, and there's no negative repercussions of sharing this stuff. They are Clojure data structures that have structural sharing, and they work just as we expect them to. But a data structure is not enough to pull this off, because if you have that, all you have is a contract for what it should do. It will not actually do that. So you need an execution environment, and that is where our other half of this comes in, where you need to have a way of running this very, very quickly. So we have an environment that takes a data structure that represents a data pipeline and its data, and it's using a snapshotting process by walking through the life cycles of its execution and denoting when values have passed through it, so you get that deep introspection back. And this is happening on every single keystroke. So that's for React, 16 milliseconds to beat the UI thread and give apparent synchronicity. And if we start to go over that, we'll fall back to a web worker, and it's still about just as fast. Like I said, this never talks to the internet. This is really the big secret to making this as snappy and as smooth experience as possible. So all of the compilation and the runtime is staying in ClojureScript. And the benefits are huge, not just to the client, but also to us as a company, because we have no server load when this happens. Like if tomorrow we had 1 billion users, all we need to do is serve the runtime out of cache. I mean, granted to say if they're just using the simulator and not actually deploying this stuff. Because the simulator just stays in JavaScript, so all we had to do is serve the runtime from cache, and we're golden. That has no server load for us, so that's great. Offline mode, I mean, it would need some polishing, but the fundamental technical challenge of getting this done it was trivial because it was just part of the game. This was what we wanted to do, is to be able to have synchronous behavior in JavaScript. Maybe the most fascinating piece of this is that your sample data has never left the browser because your code has never left the browser. And so you have data that you are mindful about being sure where it goes. It will stay in your browser when you use this approach. And so that's a nice property. I have assumed many things, somewhat because I knew I would run out of time early. But if I was just going to clarify things really quick, the key to all this is that Onyx is really two things. It is a model for creating distributed data processing programs, and it's also an execution environment for those models. I get asked a lot, why would you build a separate execution environment for this? That's a huge undertaking. Why not take Onyx's data model and then run it on Spark or Storm or Flink? And the reason is that you would have trouble building something like this, because this was really always the target. You need something that's going to be amenable to execution across different host environments. Now, the models in Onyx are actually 100% data structures, so those correspond to the things that the compiler is working across. And over the last year, we've slowly been converting Onyx to CLJC. All of the parts that have nothing to do with networking, that don't have to do I/O, all of the things that get you the right answer with Onyx Core are now in CLJC, which has allowed us to produce Onyx Local RT, which stands for runtime. And that is a pure stateless implementation of Onyx that has very heavy code sharing with Onyx Distributed. And that is one of the reasons that we get really good parity, because we're using roughly the same code that has been tuned, that has been tested, And so local RT is, for the most part, a breeze to maintain because the code sharing is so heavy. And so those are the two pieces that have enabled the compiler and the runtime. Our architecture is compilers and decompilers all the way down. What we saw was one representation for building a pipeline that has a corresponding compiler and a decompiler. And what we're going to do is take that representation, turn it into an Onyx job, and hit an optimizer. And if we wanted to, we could go in the reverse direction, with the end goal of having multiple representations. So if you don't like our in-browser way of building pipelines, you can use our HTTP API, which has its own compiler and decompiler. We also have a SQL representation. Now the magic is that you have a lingua franca in the middle, which is Onyx. It is a data contract. And so you have equivalencies across each of these things. So if you want to switch modalities and say, cool, that pipeline representation in the browser was nice, I'd like to switch to SQL, we can just round trip from one of these things to an Onyx job and then decompile back, and you're going to get the right answer because the compilation model has contracts. About a year and a half ago at the Conch, when I was introducing Clojure, I noted that what we needed here was more compilers to make this interesting, and that is the top half. We have compilers that turn pieces of data into an Onyx job. What I didn't talk about was where we run them. So this is now a many-to-many relationship where I have many kinds of expression modalities, and I also have many ways of running them, because I can turn into an Onyx job which will run equivalently either on an Onyx cluster in full distributed mode or on Onyx local RT. And so this is really the ultimate. If you can get here with your infrastructure, the flexibility is just enormous. So I've been saying that this has been ready or almost ready for a long time now. It's a big, ambitious system, and I think we are almost there at this point. So if you're interested in checking it out, just hit me up. We always like beta customers. I just wanted to thank my team. I know that I'm up here, and sometimes I get a lot of just kind of the public face of the project of Onyx and now of sort of Pyroclast. But these are the people who work extremely hard to make this happen. This was an incredibly ambitious goal, and I think when you get a set of people together who really believe in something and want to work really hard, you can do just about anything. And so these are the people who really have pulled it off. That is all I have.